Let's take a look at another kind of a material example. In this case, it's a tie rod. Okay, we want to have a strong tie rod of length L and with minimum mass M, and the cross-sectional area is A. This is circular cross-section. Rho is the density as before, and now we are going to look at the yield strength. Okay, and the constraints are that for a given length, it must not fail under the applied load F. And so for that to happen, force over area should be less than the yield strength of the material. So that's the equation for constraint on how big or small A can be. Objective, right? You want to minimize the mass. If you end up increasing A, you will have the stress always below the yield strength, but that will also mean that you'll increase the mass. So how do you end up finding a way to balance out those competing requirements for what is A? So again, we eliminate A from this equation, and when you rearrange terms over here, you will have M as force times the length, so loading parameter, geometry parameter, and this material parameter, which is rho by sigma y. As before, we choose materials with the reciprocal of this term, so the materials with the largest value of yield strength over density. You can also, as another variation of a property chart that can routinely be used in design, we can go to plot Young's modulus as a function of the strength of the material. Here you begin to see in this particular case that metals dominate the upper right corner to the greatest extent. Carbon fiber reinforced plastics end up becoming a suitable material as well. So the contours of yield strength, or yield strain rather, sigma F over E, the slope over here, appears a family of parallel straight lines. And you see there are different values of these slopes based on the design guidelines. We will delve into that to some extent as we go forward. But basically, at this region over here on the top left of the plot, you have yield occurring before buckling, and in the bottom you have buckling happening before yield. So question out there to look at is, if you want to make springs, steels and elastomers are both good for that purpose. Right? Two completely different material characteristics, material properties. Why do both of them end up being good candidates? Something to think about, and we'll revisit that over time. Another variation is specific modulus. So E over rho, which we looked at as a material index before, plotted against specific strength, sigma F over rho. And now you begin to look for design of moving components where you can maximize rotational speed or energy storage. How is that implemented? Something to look at. But these property charts will come in handy for something like that. This plot allows us to provide a measure of the least material to do the most structural work. And you can see that the composite become even more of a priority than before. Metals overall have now moved down in priority. Ceramics have increased, but given the fact that they're brittle materials, they tend to be of less direct applicability despite the predictions from these property charts. And that's something else to remember. But overall, polymers become almost as competitive as metals. Why? Right? Some things to think about. The high density of metals. Right? So you're looking at specific strength and specific modulus. So higher values of rho ends up reducing those ratios. Lower values of rho end up increasing those values, and so polymers end up improving in consideration criteria. Because of the fact that you get a combination of properties with fiber reinforced plastics, especially carbon fiber reinforced plastics, they end up becoming important candidates used in demanding applications in aerospace, where fuel efficiency, for instance, as well as structural integrity are important criteria for performance. In designs, A property chart consisting of fracture toughness plotted against Young's modulus is also quite useful. So the resistance to catastrophic failure, the resistance to the propagation of the crack, that is what is measured by fracture toughness. And so typically metals are always the major standard for being able to do that. But here are some interesting things that you can look at. If you look at the slope being an important parameter, and then depending upon the design guidelines, the value of these slopes can be quite different. It turns out that when you consider aluminum and polypropylene, you see something interesting. Although the modulus of aluminum is much higher and fracture toughness is also much higher, that ratio that we are interested in terms of the material index ends up, if you end up plotting this, you'll find out that polypropylene almost falls in the same line as an aluminum alloy. Why does that happen? Right? And so what does that mean in terms of selecting polypropylene compared to aluminum for applications where the definition is based on the values of this slope? Just like you plotted fracture toughness against modulus, you can also plot fracture toughness against the strength at the elastic limit. And if you begin to see that, this provides a chart for safe design against fracture. So the safe design of load-bearing structures, so that if something occurs in terms of a defect or a ding or a damage, the whole load-bearing structure does not completely collapse. The materials at the bottom right yield fracture before yield, and the materials over here tend to yield before fracture. Again, depending upon different design criteria, these slopes will change. Interesting to see that you really don't want to deal with foams for these kinds of situations, and metals tend to be something that do a lot better than any of the other combinations, and ceramics end up doing really bad. Coefficient versus so loss coefficient, what is that? Right? We looked at the propagation of sound and its dependence upon modulus and density. So the loss coefficient gives a measure of damping properties. Low damping materials are useful as springs. High damping are used for reducing vibration in any system.